Thank you once again for inviting me to talk to you about my favorite subject, the sun. When I was a teenager that I first came to the Hampshire Astronomical Group and caught the astronomy bug. And now 55 years later, I'm still not cured. You know, something very strange happens during the period that the sun goes dormant round about the time of solar minimum. It doesn't produce very many sunspots, and what sunspots it does produce are weak and small and short-lived. Now, sunspots are manifestations of strong magnetic fields, and in order to produce flares, the sun needs strong magnetic fields. So if there aren't many sunspots around, you don't get many flares. So at solar minimum, there are very few flares. In fact, you can go a year, maybe 2 years, without seeing a significant flare on the sun. That doesn't mean there aren't any magnetic fields on the sun. If you tune your telescope to hydrogen alpha, that's at the red end of the visible spectrum, you see these dark structures crisscrossing the surface of the sun. These are called filaments, and what they are is dense, cold material suspended above a magnetic neutral line. So when you see one of these things, you know there's positive on one side of this neutral line and negative magnetic flux on the other side of the neutral line. Now these magnetic structures are of course anchored in the photosphere, and as we all know, the photosphere is roiling around with convection cells in the form of granulation and supergranulation and things of that sort. Now that takes the foot points of these structures and mixes them up and stretches them around such that they add energy. Also, these structures are fairly large, and so they are subject to differential rotation, namely that the equator of the sun is moving faster than the poles of the sun. So they get stretched and deformed in another way. As this process carries on, these structures become more and more unstable and eventually erupt away in the form of a coronal mass ejection. Now, these coronal mass ejections are much less common at solar minimum than they are at solar maximum by over an order of magnitude. But some of those coronal mass ejections do happen at solar minimum, and some of those can actually strike the Earth. When they do, they create geomagnetic storms. Now, geomagnetics aren't only caused by coronal mass ejections, they can be caused by high-speed solar winds. And at solar minimum, the north and south polar coronal holes are at their largest and strongest. There's also quite a fair few number of coronal holes at lower latitudes. So the Earth periodically gets bathed in one of these very high-speed solar winds. And so consequently, that will create a geomagnetic storm. Now, these geomagnetic storms aren't the rip-roaring sort of geomagnetic storms that destroy satellites or make our power grids go down. These are the sort of geomagnetic storms that create nice aurora at high latitudes. And none of this is surprising. We've known about this for decades. What is surprising is what solar physicists do about all of this. After all, they've got no sunspots to look at, no flares to look at, and no major geomagnetic storms to explain away. So what do? Do they take a couple of years of vacation, write a book? Perisher thought they would spend more time with their students, but no. Surprisingly, this is a time of frenzied activity in the solar community, with just about everybody worth their salt is trying to predict the timing and amplitude of the next solar cycle. And we're in that silly season now. So we get hundreds of these presentations and papers about the upcoming cycle, and they have one thing basically in common. They're wrong. And the few that are right are probably right for the wrong reasons. That tells me that we don't know as much about the solar cycle as we like to think we do. So today I'm going to bring you the opportunity to become a fully qualified solar cycle forecaster. By the end of this talk, you should have every much as bit of chance of forecasting the solar cycle every bit as well as the professionals do. I'm going to introduce you to the dark art of forecasting the solar cycle. Well, what are the forecasting tools? Many of those tools are available to you. What do we know about previous cycles that might be relevant at forecasting the upcoming cycle? How well did we do last time around using those forecasting tools and the data that we have available? And spoiler alert, we didn't do very well at all. What do we know about solar cycle 25 so far? Wait a minute, we're already in solar cycle 25. Solar cycle 25 started in December of 2019, so we've been experiencing solar cycle 25 for just over a year now. So what have we learned about solar cycle 25 so far that might indicate that whether solar cycle 25 is going to be an active cycle or yet another low cycle? And to add piquancy to all of this, there is a a group of people that are forecasting a grand solar minimum, and then go on to claim that we're going to be catapulted into a new little ice age. So we don't need to worry about global warming. We're not going to all burn to death. We're going to freeze to death and starve to death because we'll be in an ice age. What are the tools of the trade? Well, the first tool is available to everybody. Guesswork. It could be educated guesswork, but it could still be guesswork. You know what the last cycle was, 120. Are you going to guess that it's bigger or smaller? And if so, by how much? It's sort of rather like guessing the numbers for the lottery. A bit more sciencey than that is to actually use numerology. Our brains are wired to look for patterns. If you give a group of people a set of numbers and say there's a cycle in here, find the patterns and predict the next one, everybody will come up with a number. Now, you'll probably all come up with different numbers. In fact, that might be a very interesting thing to do within the Hampshire group itself, which is to hand out copies of the amplitudes and timings of the previous 24 cycles and see what people come up with based on purely that, the size of the next cycle will be. And I bet you there'll be, if you hand out 100 versions of that, there'll be 100 different answers. Well, if we aren't smart enough to do it, perhaps we could get our machines to do it for us. Artificial intelligence, computer learning, neural nets. Basically, you give the machine a series of parameters and say, using the parameters from the first one to predict the second one, now use those parameters you derived to predict the third, and adjust it according so it matches the third, and so on. That's a very crude way of putting it. It turns out the results from those aren't particularly better than the first two. What makes me conclude there is that our machines have the same problems that we do in regard because we're programming them. They can just make the same mistakes as we do, but they just do it faster. Then we get a next level up, mathematical modeling. You can use principal component analysis, Fourier analysis, or any one of 100 other mathematical tricks to try to determine what the pattern of solar maxima are over the years and predict the next one. And again, it doesn't produce anything particularly better. Then the last one is to use physical clues. One of them that's quite often used is the polar magnetic fields, or what the level of solar minimum was. Everybody else. Now, everybody using these different methods claims that they have reproduced the results to within an gnat's whisker, particularly after the event, but actually during the event is not quite so well documented. What's the way forward? Helioseismology, I think. There we use the vibrational states of the sun. We look at how waves are propagated around and through the sun and use that like a seismograph does on Earth to look at the internal structure of the sun. And if we could get fine enough fidelity on those images, we might be able to see the beginnings of the upcoming solar cycle. The problem is, at the moment, we're very data starved. The instruments that are currently looking at the sun from a helioseismology point of view are only looking at half the sun. So we don't got half of our, or about less than half the sun. We're not seeing all the data from our objects. So that's difficult and awkward to begin with. And we don't have the time resolution or the time coverage to get all the different modes that we need to look very deep inside the sun, or to get the spatial resolution to start seeing the development of the next cycle. To do that might be decades away. And once we do, the goal of it will be to produce a three-dimensional time-dependent solar magnetic dynamo model. And then what you would do is you would plug in the current state of the dynamo and run that model forward, and that would give you a good idea of what the next solar cycle would be. But that is a massive effort. Well, what's our basic data? We're going to use sunspot data today, and we have 400 years worth of sunspot data. The trouble is, not all of the data is as good as the rest. We ignore basically the first 150 years. Why do we do that? Well, that was taken with inferior telescopes, and also the frequency of observation was not very high. So we have a situation where if you added that data into overall analysis of the other 250 years worth of data, you'd probably be adding more noise to the result than you would be adding additional signal. It also has the added problem that we have the Maunder minimum in there. And any of these cyclic models would have a great deal of difficulty of getting into a Maunder minimum, and once into a Maunder minimum, getting back out of it again. So that would affect all these other observations quite significantly. So people try to avoid that. So we have 24 cycles that we have complete data for. But even so, the further you go back in time, the less fidelity there is on the data. So the error bars on some of these earlier things are larger than the more recent ones. Well, when you look at the blue data here, you see a beat frequency. You see something that looks very, very regular. And that screams to you, oh, we can predict that. And we've been trying to do that for over 200 years, and we still haven't made very much progress. So there's something more to it than that. First problem is it isn't exactly 11 years. It changes. It could be 3 or 4 years shorter, or it could be 3 or 4 years longer. So that's another thing we have to worry about, is the change in the rate of the solar cycles. We also have an amplitude to worry about. If you leave them on the minimum, which I do, you can have amplitudes everything from near 0 to over 300, which is a very large range to have to deal with. There may be longer cycles. Some people have postulated longer cycles. We know there's a 22-year magnetic cycle. I'll mention that in a minute. But there's also other cycles. There's the Gleisberg cycle, which is anything from 80 years to 100 years, depending on who you talk to. Most people like to put it at 88 years, just making it 8 solar cycles. And they also claim there to be 200-year cycles, 400-year cycles, 800, 1200, all sorts of 100-year cycles. And I see very little evidence of any of these. This dark line here is a smooth sunspot number where we've smoothed it by an 11-year smoothing period. And so this is the average sunspot number as a function of time. And I don't see an 88-year period in there. I don't see a 200-year period in there. I don't see any periods in there, really. Any stable periods in there. So these longer cycles I take with a huge pinch of salt. And the other thing is we've only got 24 samples of the solar cycle. We may not have sampled the full range of parameters yet. There may be shorter or longer cycles. There may be larger or smaller cycles. So where does this leave us as far as our prediction is concerned? If we take these parameters, we can make a prediction. And you'll see this plot several times during the talk. What it is the predicted maximum along the x-axis and the length of the cycle along the y-axis. And given the parameters I just gave you, that would be our prediction. Now it has the advantage that it has a 96% chance of being right. However, it is not particularly useful. In fact, it is useless. How come it is useless? What do we use sunspot number for, apart from mind games with other people? Well, it actually is a useful number because it's used in the planning of space missions. For example, if you're putting satellites into low Earth orbit, you need to know what the sunspot number is during the life of that satellite. The higher the sunspot number, the larger the Earth's atmosphere warms up, and the quicker that satellite comes down. Similarly, if you're sending astronauts to live and work on the moon or Mars, you're going to wonder what time of the solar cycle do you want to send them. Do you want to send them at a near maximum, where if it's a big maximum, they could be fried by gamma rays from X flares? Or do you want to send it at solar minimum when the solar magnetic field is so weak that we get a lot more high energy cosmic rays coming into the solar system and our astronauts will die from radiation poisoning? This is something that's being generally ignored in a lot of the space planning that we have are doing at the moment and needs to be addressed. So let's contrast two successive cycles to show some general principles. These are magnetograms taken by the Solar Dynamics Observatory. The one on the left was taken during the decay phase of solar cycle 24 in December of 2016. The one on the right is the rise phase of solar cycle 25 taken in December of 2020. Now there's a couple of things that are really obvious here. First of all, the range of latitudes at which the sunspots are appearing is much narrower in the decay of solar cycle 24 than it is during the beginning of solar cycle 25. And that's perfectly normal. What happens with a new cycle is the sunspot cycle starts at high latitudes, and as it progresses, it drifts towards the equator. When it gets to the equator, it diffuses away, and the new cycle starts again at high latitude. The other thing is the polarity of the sunspot regions. In solar cycle 24, in the northern hemisphere, negative was leading and positive was following. In the southern hemisphere, a positive was leading and negative was following. And in the new cycle, that's reversed around. So we've got two methods here of telling whether a sunspot is actually from cycle 24 or from cycle 25. One is the latitude at which the sunspot appears. The other is the polarity of the sunspot region. So how well do we do predicting solar cycle 24? Well, there was 108 published papers forecasting the cycle. And this is just some of them. And there was at least twice as many presentations given, including a couple by myself. And what we have here is the forecast maximum for the cycle by each one of these authors, and they're color coded for a reason. It shows the method they were used. So say blue was a Fourier analysis, or black was polar field analysis. The thing to take away from here is that all the colors are spread throughout the whole range of predictions here. So if they're using the same data and they're using the same method, you would hope they'd get something like the same result, and they don't, which to me is also worrying. But how does this compare with what we had? So solar cycle 23 was an average cycle of about 170, 180, and so that would be there. Now note that most of the forecasts were below solar cycle 23, and they proved to be right. The solar cycle 24 came out at 120. Now, why did most of these people forecast solar cycle 24 would be smaller than solar cycle 23? It was to do with the minimum, the before the beginning of solar cycle 24. There was a very long, low solar minimum that went from 2007 to the end of 2009. So we had 3 years of very low solar activity with almost nothing going on the sun. And so that gave a big impression on solar physicists. So when they guessed their number, they thought, well, okay, it would probably be a smaller cycle than solar cycle 23. Note that most people did in fact guess that solar cycle 23 was going to be smaller than solar cycle 24. That will be important later, so just remember that. About a quarter of the people got the amplitude approximately right, allowing for the fact that some of them have very large error bars, which I think is cheating. So from that point of view, if you're getting numbers between 0 and 300 and taking a reasonable range, you'd guess about a quarter of the people will get the numbers right just by accident. People trying to guess the timing of the cycle didn't fare so well. Only 2 groups got that. So therefore, what does solar cycle 24 have to teach us? And this is solar cycle 24. What I'm plotting here is the sunspot number as a function of time. Yellow is the daily number, which varies a great deal, as you can see. There's the monthly sunspot number is the monthly average sunspot number is blue. And then we have something called the smoothed sunspot number, where you take the monthly averages and you smooth them by a 13-month boxcar. So you get a nice smooth curve, so you can determine where the peaks are and where the valleys are, where the minima and maximum are. And so let's put in where the minima were. The solar minimum between 23 and 24 was in December of 2008. The minimum between solar cycle 24 and 25, as I said, was December 2019. So we had an exact 11-year cycle. From that point of view, we have the outline of this cycle, and you can see how slowly solar cycle 24 rose. It took nearly 4 years for it to get from minimum to maximum. And it showed a minimum that was slightly less than 100. And of course, all the people that were forecasting very low minima, 100 or less, and for 18 months, they looked very good because the sunspot numbers started to drift away. However, then the sun surprised them by producing a second peak, which was larger, and therefore the maximum moved to April of 2014. Now, my colleague and I, Dr. Saber and I, had forecast December of 2013. We can see that solar cycle 25 is beginning to rise. And so I took the peak that we got in November and projected back to the equivalent time in solar cycle 24 and asked how long after minimum did we achieve these numbers. Now it took us less than a year to do this for solar cycle 25. It took nearly 2 years to do this with solar cycle 24. So solar cycle 25 seems to be rising quicker than solar cycle 25. Now there's also, as I say, this delay between these 2 peaks. Now what caused that delay? Well, what caused the first peak and what caused the second peak? The first peak was a peak in sunspot number in the northern hemisphere. The second peak was a peak in the sunspot number in the southern hemisphere. And so there's a delay between those two. And it made me start to think back then that what happens if that delay was less or more? If the delay got larger, this cycle would have been even yet lower. If it was closer together, we'd have had actually a fairly brisk cycle. And so maybe solar cycle 24 was not so much a low cycle, perhaps it was more of a spread out cycle. This happened just yesterday, by the way. I just started to look at the function of the time delay between the two hemispheres and the size of the cycle. And so I produced this plot yesterday. Now, these points aren't very well defined because I had to take them off a pretty squirrely graph. So there's fairly large error bars around each one of these. But there does seem to be a distinct relationship with the shorter the delay, the larger the cycle, the longer the delay, the smaller the cycle. Well, how much delay have we seen so far between the two hemispheres for solar cycle 25? We haven't got solar cycle 25 yet to show the delay. So we know we've got at least 6 months of delay between the two hemispheres. And if it's 6 months, then that would say that solar cycle 25 must be less than 230. We can look at probability distributions. We can take the parameters that we want to look at, the maximum amplitude and timing, and see what the distributions are. So here's the distribution of the maxima of cycles. So we have 2 cycles that had maximum between 50 and 100, 6 between 100 and 150. And so you could assume that this is some sort of Gaussian random distribution. It doesn't look much like it at the moment. So it produces so if you fit a Gaussian to it, you get a fairly broad Gaussian, which means you're not constraining the numbers very well. But you get a peak about 170 or 180. And if you take a prediction between 100 and 250, you have an 83% chance of a probability of being correct. You do the same with the length of the cycle. Now that looks a much nicer looking Gaussian. You fit your Gaussian there. It's narrower and it peaks at about 11 years. And you get a 92% probability if you forecast between 9 and 13 years. So what does that do to our forecast picture? Well, we managed to shrink that rectangle down by at least a factor of 4 here by this prediction between 100 and 250 and between 9 and 13 years. But that still, that gives you a 76% probability of being right, which is still reasonable odds, but it's not useless, but it's less useless. It's still not constraining those parameters enough to be able to start planning space missions. Well, can you use the previous cycle to forecast the next cycle? Now you could, this is cycle n versus n plus 1. You could do it n plus 2, n plus 3, or some combination of cycles, and you could play with those numbers as much as you like. But I just did, the x-axis is cycle n, the y-axis is cycle n plus 1. And you can see there's a fair bit of scatter here, which is nerve-wracking. And if you fit a straight line to it, it's not particularly convincing. There's a lot of error bars. But if you put in solar cycle 24, which is the most recent cycle, that would give us a prediction for solar cycle 25 of about 160 for the peak sunspot number. The problem is that these error bars are huge, and so this is basically useless. We're rushing towards the mean. There's a principle in math where if you have a distribution of values around some average, if you sample that distribution and you get a number that's a long way away from the average, say you make it a small, you get a small sample, say your average is 100 and you get something that's 10, the chances are the next sample was going to be bigger. It's going to regress towards the mean. Same if you get a large number, say you've got 200, the chances are the next number will be lower. And this seems to work for the solar cycles, because what I've got here is the peak of a cycle versus the size of the next cycle, the difference to the next cycle, whether it got bigger, positive, or whether it got smaller, lower. And you can see there is a sort of a trend in this, that the bigger, the smaller cycles tend to be followed by a bigger cycle, the larger cycles tend to be followed by a smaller cycle. And but there's still a lot of noise on this, however we'll put it. But so we could say, if we went to forecast something less than 150, then you would expect the next cycle to be larger. If you went to something over 200, you'd expect the next cycle to be smaller. And this line would define by how much. We put in solar cycle 24, that gives us a difference of plus 50. Solar cycle 24 was 120, 120 plus 50 is 170. So how is solar cycle 25 doing so far? Well, solar cycle 25 is beginning to dominate over solar cycle 24. What I'm plotting here is the number of new sunspot regions that appear each month, and classify them according to solar cycle 24, blue, or solar cycle 25, orange. I've got solar minimum in here in December of 2019. And you can see before that minimum, there were more solar cycle 24 regions, and they were larger and longer lived than the few solar cycle 25 regions we had. But after the minimum, the situation is reversed. There are far more solar cycle 25. It's actually taken off in a rather remarkable way than solar cycle 24. And now it's the solar cycle 24 regions that are very small and short-lived, and the solar cycle 25 are larger and longer-lived. So we see that solar cycle 25 is dominating over solar cycle 24 now. And that would imply to me the rate at which this is increasing is that the solar cycle 25 is going to be a much larger cycle. Do the same with flares. Before minimum, we only had C flares from solar cycle 24, and after minimum, we had C flares from solar cycle 25 and a couple of M flares from solar cycle 25. And again, the number of flares, an increase in the rate of the number of flares, has been quite remarkable. Now, what are these C and M flares and so on? And I mentioned X flares earlier. Well, they're an X-ray classification of flare intensity. B flares, it goes A, B, C, M, X, don't ask why. B flares are 10 times larger than A flares. C flares are 10 times larger than B flares. And those are the sort of the minimum interesting flares that you might consider. M flares are sort of flares you like to write papers about. X flares are the ones you read in the newspaper the next morning about. And we got a first M flare within 6 months of solar minimum, which is quite remarkable, because it took nearly 2 years for solar cycle 24 to produce its first M flare. So again, we're seeing more flares earlier in solar cycle 25 and larger flares than we are seeing that we saw from the equivalent time period in solar cycle 24. And so that actually says that solar cycle 25 might be somewhat larger. So can we take the rise rate of this new cycle to predict the maximum? And so what I've plotted here is the maximum of the 24 cycles against the rise rate for those cycles. And there looks to be quite a nice little tight correlation between those two, which is interesting. What's the rise rate for solar cycle 25? 40 sunspot numbers per year so far. If you take that off of there, you get a rate of 165 as the maximum. But I'm now fitting a line to a series of points, so I can actually get uncertainties on that. If I put the uncertainties in, it says we're predicting a cycle somewhere between 130 and 190. Can you do the same with the length of the cycle? Well, sort of, but not quite so good. So this is the time from minimum to maximum for the 24 cycles that we have so far. And it's no longer a linear relationship, and so it's a quadratic relationship, and there's a bit more noise on it, which is a bit more worrying. But let's put our rise rate in and see what we get. That was saying that we get the rise time from solar minimum to solar maximum for this cycle as 4 1/3 years. Again, we've put our uncertainties in there, and it comes into just less than 4 years to just less than 5 years. So I would predict, therefore, that maximum is going to be May of 2024, with about 6 months uncertainty. So this is the new prediction. The triangle is 24, so we're predicting a cycle that's more intense than solar cycle 24 and somewhat shorter than solar cycle 24, just a bit shorter than solar cycle 24. And we have a 67% chance of probability, which is a bit better than tossing a coin. This brings me to grand solar minima. Are we going to go into a grand solar minima? If all of what I've said so far, that solar cycle 25 is going to be larger, then the answer is definitively no. But there are some people that are predicting a grand solar minimum, and one of the most famous at the moment is Valentina Zarkova, and I've had a running battle with her for the last 5 years or so about this. And she has made a comprehensive model using a principal component analysis that she's run out tens of thousands of years into the future and tens of thousands of years into the past, which seems to, based on just 30 years worth of magnetic data, which doesn't seem to really make a great deal of sense, but nonetheless, that's what she's done. She's made a number of claims. She claims she was one of only 2 authors to forecast that solar cycle 24 would be smaller than solar cycle 23. Now we know that that's untrue because we just looked at that earlier in the talk. She claims that she's matched the previous cycles to within 2%. That, if she could do that, would be remarkable, and we'll take a look at that. She claims she's found a 400-year periodicity in the data. Again, from 30 years, that seems to be a little untenable. I think what she's done is she's assumed a 400-year period because everybody says a 400-year period. She claims her model reproduces major climate phenomena over the last 1,000 years. So this is linking solar activity to climate and hence to little ice ages. And so this is a controversy that has risen up, and she's got great huge following on the web at the moment, and written lots of papers about this sort of stuff, but all of them I think are basically nonsense. For why? Because all of those statements are untrue. Now let's test this idea that her predictions were about 2% accurate, which, as I said, would be remarkable if you could do it. This is her plot from the 2015 paper that she wrote about this. And this shows solar activity as a function of time for the last 4 cycles and the next 2 cycles. They're in arbitrary units, so I don't know how to scale this to sunspot number. But the one thing you can't change when you scale something is where the peaks and the valleys are. So we can look at the dates of solar maximum and the dates of solar minimum and see how accurate they are. So let's take a look at solar maximum first. For cycle 21, she was almost spot on. Solar cycle 22, she was about a year early. Solar cycle 23, just over a year late. Solar cycle 24, well over 2 years late. And so this does not seem to average to me about 2%. We can do the same thing for solar minimum. This is the blue triangles here, and that's just as bad. Now, as I say, the paper was written in 2015, so the one date she didn't have available to her was the date of the solar minimum between solar cycles 24 and solar cycles 25. And that was December of 2019. I'll mark that here with the green triangle. And you can see at the time when the sun was actually producing basically no sunspots, her model predicted that we would be already halfway to solar maximum. She then uses this to create a prediction of the solar maximum for solar cycle 25 of being next year, 2022, at a level of about 100. And you can see that that is unlikely to come true. So it looks to me as though there's some sort of phasing problem in her model that gets out further and further out of phase with the maxima and the minima as times go by. So there's a basic problem with the model. Zarkova claims she just uses 30 years worth of magnetic data to produce a model that spans more than 400 years. In fact, in some cases, spans tens of thousands of years in either direction. The black oval here is the timescale that she used her data on. Now, the way to look at this plot is that the oscillations you're seeing, the larger the oscillations are more sunspots, the smaller the oscillations, the less sunspots. She claims when there are a large number of sunspots on the sun, the climate is warm, and when there's a small oscillation on the sun, there's few sunspots, and so the climate is cold. Now, she identifies 4 dates that seemingly support her model. As these 4: medieval warm period, the Little Ice Age, the Maunder minimum, and the Dalton minimum. So let's take a look at each of those in turn. Now, these dates are in the historical record, and you can look them up yourself, but apparently she didn't. The medieval warm period is not there, it's back there. It's from 950 to about 1300. The Little Ice Age isn't there, it's from about 1350 to 1850. Which would include 2 periods which she would say would be warm. The Maunder minimum isn't there, it's there. Now, that would actually fit her model better because the amplitude of the oscillations there are very small, and that would indicate a very low level of solar activity. But if you put the Maunder minimum there, then you have to put the Dalton minimum out here in a period when she claims there was a lot of sunspots. And of course, the Dalton minimum is famous for the fact that it wasn't a lot of sunspots. So her model does not fit historical record. So that doesn't validate her model. In fact, if anything, it invalidates the model. Don't get me wrong, even though this prediction of grand solar minimum is, I think, in error, there have been lots of them in the past. How do we know? Well, we can look at the ice core records. What happens is when the sun is inactive, the solar magnetic field is weak, and it allows more high energy cosmic rays into the solar system, and they impact the upper part of our atmosphere, producing certain isotopes. Those isotopes can get trapped in the layers of ice at the poles. So when you take an ice core, you can find the isotopic composition of the atmosphere at given times. And when these isotopes are in particular abundance, we know that there was a grand solar minimum. And this is a plot of those grand solar minimum over the last 12,000 years. The grand solar minima are where these blue icicles are hanging down from the blue line. If you look at the data, there's 24 of them in the last 12,000 years. That's a rate of 1 every 500 years, not 400 years, note, on average. But you'll note that the timing of these things is not quasi-periodic like the solar cycle, which we can't predict even though it's quasi-periodic. This looks completely random. And so there's no way we can predict a grand solar minimum from data like this, or any other data for that matter. And the timing varies from anything from 100 years to 2,000 years apart. So we don't have the foggiest idea when the next one will be. It's random. And also the length of these cycles can't be predicted because they vary from 20 to over 100 years. And so trying to tell me that there's a grand solar minimum coming up in the next 10 years and it's going to last for 30 years or 70 years is plain nonsense. Well, even if there is a grand solar minimum, there's going to be no little ice age. How can I claim that? Well, you can correlate the number of sunspots against global temperatures. And I've done that here. We have the average global temperature anomaly in degrees C along the x-axis and the monthly average sunspot number along the y-axis. And you see it basically produces a scatter plot. There is no trend there whatsoever. So you know that there's no relationship between those sunspots and that global temperature. Now, you could argue there's some sort of displacement in time for these particular numbers, but you could slide these data sets backwards and forwards as much as you like, and you won't get a much better correlation than this, which isn't a correlation at all. Well, we've got a number of predictions already for this cycle, so let's take a look at some of them. Here's the one that we just produced ourselves, and this is the NASA Noaa prediction, which is very similar to solar cycle 24 and peaking in 2025. Here's Zarkova's prediction. This one is by Hathaway, one in green, which is very similar to the NASA Noaa panel, which of course is not surprising because he was on the NASA Noaa panel. Pat McIntosh is forecasting quite a robust cycle, and I hope he is right. Then we have about 38 other, and here's just a sample of them, and they're sort of clumping rather like I've shown here, around about the level of the previous cycle, maybe a little bit higher or a little bit lower, and varying in time from 2023 up to 2026. The main conclusion you should draw from this talk is the next few years is going to be great for observing the sun. So the first thing you should do is get your telescopes set up safely to observe the sun. Better yet, get an H-alpha filter, because then not only can you see those filaments that I was talking about, but you can also see H-alpha flares. Take photographs and use those photographs to make up your own sunspot number. See how that tracks with the professional level sunspot numbers that are issued on the web. You can use online resources. There's the Solar Dynamics Observatory, the SOHO spacecraft, Stereo A, GOES-R, a Solar Influences Data Center, to name but a few. Then you can follow the rise of solar cycle 25 and see if your prediction is better than that of the pros. And if you follow the instructions that I've given today, it probably will be. If you want to follow what's going on the sun, you can follow me on both YouTube and Twitter under the name DRK Strong. As far as grand solar minima are concerned, you can keep calm and carry on because it's not going to happen. Thank you for listening. And if you have any questions, please enter them in the questions box below. Thanks a lot. Goodbye.